Welcome to an overview of my experience as a Joule Fellow here at the University of Connecticut. Before I delve into my experience, here's a bit about me. My name is Ashley LePayne, and I am an 8th grade science teacher at Canton Middle School. I am also a recent graduate from the NEAG School of Education here at UConn. I designed my classroom this past year around students learning through doing science rather than me just teaching them about it. Throughout the duration of the Joule Fellows Program, we were fortunate to be able to take field trips to industries around the UConn area. From farms to breweries, each sector of our world utilizes engineers to improve society. These field trips were exciting reminders to show students that engineering extends far beyond construction or the lab. With these rich experiences, I also learned about great new technology to bring back to my classroom. I have always been interested in 3D printing and coding, but have never been able to do anything more than just read about them. I am looking forward to using SolidWorks, Arduino, and ImageJ with my students. With the feats also came the many challenges during our experience. For example, we used our Joule Buddies force sensor as a guide when designing and ordering materials of our own. The size of our Joule Buddies force sensor is seen on the left. We were quite shocked when our materials came in the mail, and we quickly realized that our force sensor was going to be just a little bit larger. It all worked out though, because we were able to test even larger samples than those in the lab. One of the other fellows summed up these experiences as just going through the engineering design process. I began to look at encountering challenges as just part of that process. For 5 of the 6 weeks, my partner Diane and I worked in Professor Hoshino's biosensors lab. His work focuses on nano and micro-scale mechanical sensing and optical imaging. They work at incredibly small scales on individual cells and spheroids, or 3D cell colonies. One focus that really caught my interest was their novel approach to characterizing the stiffness of cancer cells. Here you see the method of using cantilevers to compress the cell, as well as how software was able to measure the deformation of the cell using reference images. The overarching science concepts utilized in the lab are stress, strain, and Young's modulus. I hope to take these ideas back to my classroom to teach students to begin thinking about these terms beyond just being stressed out over a test, or that you strain your muscles when you are trying to pick up something that is too heavy for you. This led me to creating examples that can be visualized for students to understand. Stress scientifically is described as the force applied over an area. You can think of this as sitting in the middle of a pool float versus laying across the float. If you sit in the middle of the float, all of your force is concentrated in a small area and you will likely fall into the pool. However, if you lay across the float horizontally, your force is spread out over a greater area and you will likely stay dry. Strain accompanies stress and measures how much the object deforms. This deformation can be found by looking at the length before and after stress is applied. And lastly, the Young's modulus of a material can be found by dividing its stress by the strain. The Young's modulus is a property of a material that describes how stiff it is. Each material in our world has an approximate Young's modulus. Here is a sample of data obtained from our sensor. While Professor Hoshino's lab works at the micro and nano level, we magnified the experiment to working with samples that students can see and are familiar with. For example, here is a sponge used to wash cars. So how did we complete this process? We first made our many samples using various types of sponges and foams. Diane also soaked chicken bones in vinegar for 10 days to decalcify them, creating rubber bones that we can squish. Here are our samples from kitchen sponges to magic erasers. We use scalpels and calipers to make our samples as uniform and accurate as possible. And here is our extra large force sensor. Here you see the 50 kilogram load cell as well as the stepper motor on the bottom. Here is our experimental setup with the sample supported on a fixed stage. The microscopic camera captures high quality images of the process, while the Arduino controls the magnitude and direction of the motor, and the software displays images from the camera on screen. Here's what the screen looks like with the Arduino code on the left and camera software on the right. After the motor moves each step, the force is measured and displayed on the Arduino. We then tell the camera software to take a picture. We then use ImageJ software to measure the magnitude of squish after each motor movement. We do this by measuring the sample in each picture and comparing the initial dimensions of the sample to its dimensions after the force is applied. And then finally, we input all of the information from the force sensor and the measurements from ImageJ into Google Sheets to calculate stress and strain. So what can we do with all of this? Diane and I are very excited about the topic, and we think our students will enjoy it too. What I hope to do in my middle school classroom is introduce my students to how engineers analyze materials used to serve a purpose or solve a problem. I plan to teach these concepts in a scaffolded approach by first teaching students about stress and strain through a lesson. I will then utilize our force sensor to demonstrate Newton's second law of force equals mass times acceleration. Then, students will work with the content through hands-on activities in order to reach the end goal of creating a cushion device for those prone to falls, such as the elderly and athletes. I am so thankful for the rewarding experience of being a Joule Fellow this summer. I was able to put on my learner hat once again and really dive into engineering for the first time ever. I have a much greater understanding of the process, as well as the technologies and responsibilities that come with being an engineer in the 21st century. My greatest takeaway is just how much collaboration is done in engineering. The thermal grill built on the left would not have been possible without the combined efforts of 4 teachers. I also spent a lot of time collaborating with 2 high school math teachers, which I don't get to do often. The same is true for Professor Hoshino's scientists in the lab. While they might not be working on the same thing for a lot of the time, they each help each other figure things out. There's even some cross-university collaboration going on, which I think is so impressive. The brand new Innovation Partnership Building at UConn has the same goal as well. I hope that we as teachers can create partnerships with universities and industries to help promote the promising profession of engineering and get our students excited about engineering. Thank you so much for watching, and many thanks to everyone involved, especially Diane, for making my experience as a Joule Fellow so successful this summer.